So again, we're going to keep using PV equals nRT, but today we're going to start to modify some things. And what we're going to do is determine the molecular mass. In other words, when we talk about molecular mass, we can categorize it as big M, and the units for molecular mass is grams per mole. So what we'll do is we can find out how many grams we have, we can determine how many moles we have, or use PV equals nRT, which is really sweet, and it'll give us this value. One of the things that we have to realize is that when we look at N, and I'll give you this information, I think it's on the back of your periodic table as well, but the N in PV equals nRT represents the number of moles. The little m represents mass, and the big M actually doesn't represent molarity in this case, but it represents molar mass, which is this one right here. So again, what we have is the molar mass, which is in grams per mole, which is big M, and again, mass is grams and N is moles, so it's kind of a redundant statement there. So what we'll do is we'll get to use PV equals nRT in working these out to determine the molecular mass. Okay? So actually the best way is by doing an example. So let's look at the first example here. And I put number 5 on here because it's the 5th one in your packet, but it's your number 1 on page 8, 9, okay. All right, so here's the question. It asks, if 0.55 grams of gas occupies 0.2 liters at 0.968 atmospheres and 289 Kelvin, what is the molecular mass of this gas? Now, normally, if you see a mass for the gas, and I've been preaching it the whole time, you normally would change that gram amount into moles. The bad news is we don't know what this gas is, so we can't change the grams into moles. So as a heads up, if you look at a problem like this and you're like, he didn't give us a gas, he didn't tell us if it's chlorine or whatever. So don't change the grams, or don't try to change the grams in this case. So what we'll do is we'll start off with PV equals nRT, and then we will rewrite this, and we'll change the N, as we did back on the other part here. We're going to change that to represent PV equals little m over big M RT. So that's the change, or that's actually part of the lecture for today. That little n represents little m over big M. Okay? And then from there, we rearrange variables because, again, the big M represents what? The molar mass or molecular mass, however you want to phrase it, and that's what we're looking for. So if we are looking for the molecular mass, let me ask you a few questions. Do we know the P? Actually, let's go ahead and label these. So this is little m. What does the 0.2 represent here? The volume. What does the 0.968 atmospheres? Pressure. What is the 289 Kelvin? Temperature. And then it wants to know what is the molecular mass. So there it is, your question mark big M. So we know the pressure, we know the volume, we know the mass, we know the temperature, and of course the R will identify which one we want to use there. So here's what we want to do. We want to move the value that we're looking for, the variable that we're solving for, to the other side and in the numerator. So it's in the denominator, so we need to multiply big M on both sides. So now the equation looks like this, where we have big M PV equals nRT. So we multiplied the big M on both sides, so now we have this equation. Secondly, I want to get all the known variables on the same side. So what I'm going to do is divide PV on both sides. So now my equation looks like this. Big M is equal to little n RT over PV. So again, we're just rearranging the variables.
Can you just start out with that? Like,
Can you start off with this?
Yeah, I mean, like, if you know that you have to get big M, you have to go through all this.
In your mind, if you can do that, that's fine. Again, this is really the part where you must show me. So if you need to do the rearrangement, because again, we'll be using PV equals nRT for everything that we're doing. Yeah, Madison. Oh, I'm sorry. You're right. Yeah. Thank you. Sorry about that. Okay. So now we have, Yeah, the mass times the ideal gas constant, R, times the temperature divided by the pressure in the volume. Is that what you were going to ask, Marissa?
Yes.
Good call. All right. So once we have that, good news is let's plug the values in. So our mass is 0.55 grams. So we have 0.55 grams. Oop, put a 0 on there. And R, which R should we use in this case? The atmosphere one. Good. And for the atmosphere, it is 0.0821, and that is atmosphere liter. And let's put that mole Kelvin on the opposite side. Now, you don't have to memorize that value. That's always going to be given to you. And I believe it's on the back of your periodic table as well. The temperature, 289. And pressure, 0.968 atm, and the volume, 0.2. So 0.2 liters. All right, so let's cancel out units, just see where we're at. So who can cancel here? Liters can go away. Atmospheres can go away. Kelvin can go away. And is that it? What unit remains? Grams per mole, which is molar mass. So again, the units are telling you that you're at least setting it up correctly, which is probably the most important thing. So we know we have grams per mole, and then it's just a matter of typing it in. 67? Nice. Okay. Now, if it were a single element and we don't know what this is, then if I were to ask you to identify that element, go to the periodic table and look for a molar mass that's close to that. That's not what I'm saying to do, because I don't know if this is a compound or an element. Okay. So, of this gas. But the most important part is going from PV equals nRT to this equation here. I'm not going to have you memorize any of these things. I don't want you to memorize any of the equations because, again, there's so much that we can do with PV equals nRT. So please don't try to memorize all these equations. All right, so let's look at the next one, number 2 in your notes. The question says that if 24.23 grams of a gas occupies 8 liters at 1.5 atmospheres and 396 Kelvin, what is the molar mass of this gas? Try this one on your own, and don't peek up here. Give it a shot. I'll go through the steps here, but don't peek. I hear calculators going crazy back there, which is good. So again, the atmospheres can cancel, liters, Kelvin. So it gives us grams per mole. Anybody get a value? 65.7. Anybody else agree with that?
65.6.
Tomato. We can live with that. And again, if you had 65.6 and somebody else had 65.7 and you showed all your work, that's what I'm interested in. So again, the setup. Again, this top part right here, these first two lines, this is, maybe some of you need to write it on paper, some of you can do it in your head, but the part that I must see, the variable you're solving for, the variables rearranged, the values plugged in with the units, and of course your answer. Okay? All right. So not too bad. What's that? It is easy, yeah. Once you know how to do it, of course. All right, gas density. Okay. Gas density is similar, and realize we talked about densities at the beginning of the year, where density is the mass over the volume. So we can find out what the mass of a gas is over its volume and determine what the density is. So, I mean, nothing really spectacular there, except we are still changing the n into little m over big M, and then we rearrange the variables so that we get, as a result, we get m over v, which is equal to density. So that's what the variables that we're rearranging to look for. So let's do a practice problem. Okay, and I think I show the process of going through that. Okay, in the notes. So number 7 says calculate the density of hexane gas, which is C6H14, in grams per liter, 35 degrees Celsius, and 1.375 atmospheres. And as a hint, I put on here, calculate your molar mass first, because we don't have the molar mass. In other words, it's nice to know some values that are involved here. In other words, if I didn't give you what the molar mass was, I was going to have to give you a lot more information. So let's find out what the molar mass for hexane is. So C6H14. How many carbons do we have? 6 of those. And the molar mass for carbon is 12.01. And then we have 14 hydrogens. And hydrogen is 1.008. So let's get a value for that first. So around 86.172. Anybody get that? All right, now, I know and I realize that whenever I work out molar masses, I always go with just grams. But really, what do these masses represent? If I had carbon, I have 12.01 grams for every mole. Very good. So your units really look like that. It's grams per mole. And again, this is why you want to be really careful with your units, because that represents M. Okay? So you have your big M. You have your grams per mole. So we have our big M. We have our temperature, which is, what is that? Was that 308? So add 273 to that. Is that 308? Okay. And we have our pressure. And so it's asking for the density. So let's go ahead and write out PV equals nRT. And then we will change PV equals nRT to PV equals little m over big M RT. So we can substitute the little m over big M for our number of moles. Now what we're trying to do is we're trying to get density. And density, again, is mass over volume, which is your density. Now, we're not going to use the letter D as in dog here. I don't want to see you write D. Don't do that, okay? But more importantly, I want you to get your variables to look like that. So what we will not do is we won't move little m, but we will move the volume. So we're going to divide it on both sides. So now our equation looks like this. RT over big M and V, okay? Now again, what we're trying to do is we're trying to isolate just the little m and the v, so now I need to start moving the other variables to the other side. So that means I need to divide r and t on both sides and do what to big M? Multiply it. Okay. So again, That leaves mass over volume, which is your density. So after I multiply big M on both sides and divide RT on both sides, I get MP over RT, which is little m over V. Okay. So again, I started with PV equals nRT and I finished here. Once I do that, plug and chug. So you just found the molar mass, so let's go ahead and plug that in. Let's see if we can move this around a little bit. I'll bring that over. Okay, so the molar mass we said was 86.172. So 86.172. And what are the units for that again? Grams. And I'm going to put moles right there. Okay. So it's grams per mole. Don't put a second division line in there. It's grams per mole. All right, and then the pressure, what was the pressure? 1.375. So 1.375 atm. Okay. So I have my molar mass and I have my pressure. The R, which R should we be using here? The atmosphere one. Good. So I'm going to go 0.0821 atmosphere liter, and I'm going to put the mole Kelvin right there. Okay. And temperature. 308. We changed the 35 degrees Celsius to 308. So we'll plug our 308 in. Okay. And let's see what values can cancel. Who can we cancel here? Mole. We can get rid of moles. Okay. What else? Kelvin. We can get rid of Kelvin. Atmosphere. Get rid of atmosphere. What unit remains? Grams over liter. So we have a mass over a volume. Hey, the units are telling us we're doing this right, which is good. So we have grams over liter. And I'll admit, we haven't seen that unit before, but again, it's a mass over volume type unit. And then whatever the numbers give us. 4.69. And that's grams per liter. Okay. So not too bad. So as a hint, make sure that you find your molar mass, because really that variable wasn't given to you in this problem. So we need to find the molar mass if you're looking for a density. All right, let's look at the last one. Okay. And actually try this one on your own. So let's see. Didn't find oxygen gas. Anybody get a number?
1.26.
1.26? Thank you. Okay. So not too bad. The threes are your homework.